Okay, a quick example here where I'm going to look at a situation of thin film interference. We're looking at a soap bubble suspended in air here. The soap bubble is reflecting a lot of green light. You see this if you're washing dishes or something. You see like a color in the soap bubble that you're looking at. And the reason that that's happening is because the soap bubble happens to be just at the right thickness to constructively reflect that color that you're observing. So I'm just going to come up with some possible thicknesses for the soap bubble, and I'll just pick a few random things to work with. We're not going to know which of these it is, we'll just know it's one of these. So again, here's our situation. N equals 1, that's the air, and then the soap bubble is suspended freely between the air. So it's like that. And again, I'm going to draw these two different possibilities for the travel of the light off of each other so that I can see them, but really remember these should all be directly lined up, one right on top of the other. Then you wouldn't be able to see what I was doing. I'll call this one 1 and this one 2 to represent the light that does not go into the film and the light that does go into the film, and I'll call the thickness of the film T. Now for L1, I don't have any T contribution because it doesn't go into the film at all. I'm going from a low to a high refractive index on that barrier, and 1 equals 1, and then 2 equals 1.33. So I do have a phase shift associated with the fact that it's a fixed end reflection, so I'll use lambda on 2. For L2, I'm going to go from this into the film this time. I go thickness 1 on the way down and thickness 2 on the way up, so I get 2T. Here, I'm going from a refractive index of 1.33 to a refractive index of 1. That's a free end reflection, and so I do not get any contribution. I do not get any phase shift associated with that. So here, remember, N2 was greater than N1, so this was a fixed end, which means we get the inversion of the pulse. And here we're going from N equals 1.33 to N2 equals 1, so N2 is less than N1, which means it's a free, which means no inversion, which means no lambda over 2 here. Okay, so L2 minus L1 works out in this case to be 2T minus lambda over 2. And I'm saying it's reflecting a lot of green light, so this is going to be my constructive situation here. Careful with these ends. There's lots of ends going on in these different situations. N is used both for refractive index and as a counter in this. It's a little annoying. Maybe we should have chose something different for the counter variable, but that's what they did. So I don't know. We're kind of stuck with it. Anyways, remember this is a counter or an integer. Integer, if I can spell. And these ends here refer to refractive indices. Now, before I can use this equation, I need to be a little bit careful and remember that since my interference is occurring inside the film, I can't use the wavelength in free space. I have to adjust for the refractive index of the film. So here I have a 540 nanometer wavelength in free space inside the film. I have a refractive index of 1.33. So my wavelength inside the film will be about 406 nanometers. I'm rounding that number. Okay, now go over here, and this integer can be any integer. So I'm going to just choose some. Remember it said determine some possible thicknesses for the film here. So I'm going to just choose a few n values and solve this equation for them. And then those are just some possible thicknesses. So let's do n equals 3. Why not? So 2t minus lambda over 2 is going to be equal to 3 minus 1 lambda. So 2t minus lambda over 2 is equal to 2 lambda, and 2t then is going to be equal to 5 lambda over 2, or 2.5 lambda if you prefer. If you want to go 2.5, whatever, it doesn't matter. And then t is equal to 5 lambda over 4, and so that I can stick my actual value for lambda in. 507.5 nanometers. So a film with that thickness would create a constructive interference situation for green light, and as a result, if that soap bubble existed in air and regular light was hitting it, we'd see just green light being reflected because it'd be reflected at a higher intensity than the other lights that were hitting it. And the soap bubble would be pretty and it would be green. L2 minus L1. Oh, hold on. What if I want to do some other n value? Let's do n equals 5, no good reason. 2t minus lambda on 2 equals 5 minus 1 lambda. So if I work all the way through that, I get to 9/4 of the wavelength in the film, and I get a thickness of 913.5 nanometers. So what's the point? 507.5 nanometers isn't the only wavelength of light that will reflect really well or reflect constructively for green light. We could also have 913.5 nanometers. In fact, you can imagine, because we have an integer in this equation that we can change, we could come up with a whole lot of thicknesses for this film. And if you actually thought about it, it's going to end up being an arithmetic sequence, and you could, whatever, figure that all out. In the end, if the soap bubble happens to be this thick, that's why it would glow, or it would almost appear like it's shining green. And that's what you're observing when you observe colors in soap bubbles. Okay, I'm going to do one more example where I'm going to do reflection coating on a mirror, and that'll be that.